For our final talk of the session, we have Jenny Lemire, who just graduated with a PhD from Cornell and is on the job market for industrial or academic research positions. And he's going to tell us what he's going to talk about.
Hi, thank you so much for that introduction. Once my slides are up. Whoops. Yeah, I'm here to talk about Shale, which is a practical, scalable, Oblivious reconfigurable network. And actually, a lot of the talks we've seen so far in the session are about Oblivious reconfigurable networks, and a lot of the motivation is kind of shared. But I'm going to start by motivating why do we care about Oblivious reconfigurable networks? Well, we all know our data center networks demands are growing exponentially. Google reports that their bandwidth demand in their data center networks is doubling almost every year. Microsoft has shown similar scaling in their data center networks. The link rates that they're deploying have increased by 400 times in 10 years. But at the same time, the actual switch chips that we're using to implement our networks, they're doubling in speed every 2 years, which is corresponding to Moore's law. And it's a bit worrying that even this slower scaling might be hard to keep up because the semiconductor industry is kind of having trouble keeping up with Moore's law lately. So this motivates us to look at, the alternate switching technology of circuit switches, and they have a number of benefits that, you've heard throughout the session. First of all, when we're sending data in light form, it can remain in light form as it traverses a circuit switch, which is really nice. Additionally, not only are they not limited by Moore's law, but you can actually kind of use the same switch in many cases, even as you upgrade the surrounding network, so we're completely eliminating the switch as a barrier to scaling the network rates. But they are kind of annoying to use because you have to actually instruct them which circuits to set up. And in addition, it used to be that circuit switches were really slow to reconfigure. And this was a huge barrier to using them in data center networks because they were really inefficient for most of the traffic, which is often short flows. But our work is motivated by recent demonstrations of nanosecond scale optical circuit switching. In particular, I want to bring up Project Sirius by Microsoft Research in Cambridge as one really prominent example of this. This motivates us to ask, can we now design a data center network that uses only these nanosecond scale reconfigurable circuit switches and can support all the traffic, including low latency traffic? So the normal way that we would design a traditional circuit switch network is we kind of try to collect information about what the current demand is, and then we try to compute what are the best circuits that we should deploy right now. And this entire process takes some time. And then we inform the switch and we can actually deploy the circuits and send data. But when our switch can reconfigure in just a few nanoseconds, this beginning part where we try to compute the optimal circuits is too slow. So these traditional designs are usually not going to work for low latency. So that motivates us to try and reconfigure the switch oblivious to the traffic. And that's where oblivious reconfigurable networks come in, where instead of reconfiguring dynamically, instead we pre-schedule the circuits that we're going to have at every point in time, and we just kind of iterate through the schedule. And if we have a nanosecond scale circuit switch, we only have to be in any one of these reconfigurations for like maybe a couple of tens of nanoseconds, and that's sufficient to amortize the reconfiguration time. So we can iterate through the schedule very, very quickly. And there are existing oblivious reconfigurable networks that have existed for a while. I want to highlight RotorNet, Shale, and Sirius, which all use a similar schedule, which is just one big round robin. We've seen talk about this throughout the session. And the way a round robin schedule works is every node kind of connects to every other node once. Here, let's see this toy example with 5 nodes, and we can see that each node connects to every other node once. And the way that you can send data on top of such a network is something like this. Let's say node A wants to send to node B. In the first time slot, we're directly connected to node B, and we can just send to it. But most of the time slots, we're not connected to node B. So instead, what we can do is we can send indirectly via whichever node we're connected to right now, and eventually forward it to node B. And this is an example of something called Valiant load balancing, which is where you send traffic via these intermediate nodes. And the reason we do this is because it unlocks all of the bandwidth for us. We can use all of the bandwidth even if we have a very unbalanced workload. And that means that these existing systems are able to always guarantee us a throughput that is at least half of the line rate, because half of the hops are those first spraying hops to reach the intermediate node, and half of them are the direct hops to reach the destination node. So half of those hops are actually giving us destination throughput. At the same time, though, although this throughput is like really nice and high for ORNs, the latency is not that great. It's O of n. So to look at this cell that we sent via node D has to wait an entire iteration of the schedule before it's able to forward to node B. And that's fine if you only have 5 nodes, but if you have a data center with like hundreds of thousands of nodes, this is not very good. And if we use the time slot length that Shale uses, for example, which is about 5 nanoseconds, we use a similar time slot length in our evaluation, even with that fast time slot length, it's still going to take you about half a millisecond in latency, which is getting you right back to where we are with our traditional circuit switch designs. And additionally, you have to maintain network state for all of those 100,000 connections you're going to make over the course of the schedule. And we found that this requires potentially multiple gigabytes of on-chip memory in order to maintain all of that state. So can we do better than this? Can we actually change what we're doing and make a more scalable ORN? That's what we try to show in this work. A good slide to pay attention to is our contributions. We designed Shale, which is a new ORN that actually can support data center scales with tens of thousands or even 100,000 nodes. It achieves orders of magnitude better latency and memory requirements than existing designs at these scales. It does this by using new schedules that bring a tunable trade-off between the throughput and the latency in order to enable these schedules to actually work practically. And also all of those trade-offs is a Pareto optimal trade-off for ORNs. We've shown this in a previous theoretical work. In order to enable this, we designed a new congestion control which works for Shale's unique context. And we have an FPGA-based hardware implementation that shows that you can actually do this practically and also proves that our memory requirements are in fact reduced. And at the end, I'll try to talk about interleaving and how you can combine multiple tunings and kind of get the best of low latency and high throughput at the same time. So first, let's talk about Shale's schedule. We generalized the existing big round-robin schedule, and each node, instead of participating in just one big round-robin with all the nodes, it's going to participate in several smaller round-robins controlled by our tuning parameter h. So let's see this visually. Here's the single round-robin from before. And to make the rest of this section a little easier to understand, I'm going to focus on just one node. I'm going to focus on node A, and here it is doing its round-robin. You can see here it is connecting to each of the other nodes once. And now let's look at an example with more nodes. We can see node A is going to connect once to all of these other 15 nodes. And now let's rearrange the nodes into these groups of 4 nodes. And I'll also relabel the nodes and color them different colors. And now I can show you the Shale schedule for h equals 2. Looking at node 0, 0, it's first going to do a round robin with the nodes in the same box, and then it's going to do a round robin with the nodes in the same color. So box and color. And in the first round robin, you'll notice it's connecting to nodes with a differing x coordinate and then to nodes with a differing y coordinate. So a direct path in Shale with h equals 2 is going to take 2 hops, one to set the x coordinate and one to set the y coordinate. And in general, a direct path in Shale is going to take you h hops, because h is the number of coordinates that each node is going to have. We still want to use valiant load balancing, so a full path in Shale is going to look something like this. Let's say we want to send from node 0, 0 to node 3, 2. We're first going to take 2 spraying hops, one on each coordinate, and these are randomly chosen, and we reach our intermediate node. And then we take 2 direct hops to finally reach our destination. So by doing this, we achieve a much better latency than the existing designs. Instead of being O of n, we are now O of square root n or O of cube root n, depending on what we set h to. It's a different root of n. We did make our throughput a little bit worse because we are now using more hops in our path. So in order to understand if this trade-off is good, let's put some actual numbers to this. So here is a graph of different tunings of Shale for 100,000 nodes. On the x-axis, we see the throughput. We want the throughput to be high. On the y-axis, we see the intrinsic latency, or the latency that's purely due to the schedule and the routing scheme, ignoring queuing and propagation delay for now. And we want that to be low. Also note that the y-axis is on a log scale. We want to have high throughput and low latency. So the existing designs have really bad throughput. They have really bad latency, sorry. They have a latency of 100,000 time slots at this scale. And if we use the same time slot length that we use in our evaluation, we see that that's over half a millisecond. Just by going to Shale with h equals 2, we get almost 2 orders of magnitude improvement in the intrinsic latency. And then if we go to h equals 4, we get almost an additional order of magnitude improvement. So this is a very interesting trade-off. Even though we're sacrificing some of the throughput to achieve this, we're getting orders of magnitude better latency. But now let's talk about some of those other sources of latency that I avoided before, namely queuing. So here's going to be an example of how queuing can happen in an unexpected situation in Shale, where we have these 2 different cells that are headed to different destinations and are coming from different sources. But if we happen to spray them to the same intermediate node, it turns out that they want to take the same direct hop as their next hop, according to Shale's routing. And what we have to do is we have to pick one of them to send first, and the other one will just suffer some queuing delay. Except the orange one actually finishes arriving before we even have a chance to send the red one, because queues in Shale are draining a lot slower. We have to wait an entire iteration of the schedule before we can send that red frame. So this is an example of a big problem throughout ORNs, which is that queuing actually has a much larger impact in this context because queues only empty once per schedule iteration, not at line rate. An additional issue here is that we need to use a huge number of paths even within the same flow. In our previous theoretical work, we really showed that you really need to use valiant load balancing here and do packet spraying. So that means that a lot of existing data center congestion control doesn't quite fit in this context. Existing ORN designs had a really elegant approach, but it was tied to their two hot paths. Shale has longer paths, which pose a difficulty because the congestion can occur far from both the source and the destination. So we need to take a different approach here for our congestion control. And we're going to consider two types of congestion, and we're going to use different strategies for each. First, there's path collisions, where you have different different destination cells that happen to have contention over the same link at a given point in time. And then we're going to have egress congestion, which is when you have something like incast and there's a lot of cells headed to the same destination, and they kind of pile up in the final queues headed towards that destination. So first, path collisions. The way that we address this is with a strategy we call spray short. This eliminates some of the path collisions. Let's say, again, we have this orange cell that ends up at this intermediate node, and it wants to take this hop next. This is a direct hop. And let's say we also have this red cell, which ends up at this same intermediate node, and we now want to take a spraying hop on the x coordinate. Now, if we're doing pure valiant load balancing, we choose this randomly, and we might choose this one. And that one's a bad one to choose, because if we pick it, we'll have queuing delay. So instead, what spray short says is don't pick a random one, pick one that has a shorter queue. So we're no longer doing pure valiant load balancing, we're now picking shorter queues to send for our spraying hops. And although it's not pure valiant load balancing anymore, we actually get much better performance out of doing this. And in our paper, we have some intuition as to why it's actually not a problem that we're not doing pure valiant load balancing anymore. Next, let's talk about how we address egress congestion. Here we do a hop-by-hop congestion control mechanism. And the way that this works is when we send a cell via a given path, we're not going to send any more cells that are going to traverse the same path via that same intermediate node until we receive a token back from that intermediate node. And the intermediate node is going to send us that token once it has sent that cell on the next hop. So for example, let's say we're sending cells from node AA to node CC, and we're happening to send them along this path. Once we send a cell on its first spraying hop via node BA, node AA is not going to send another cell destined to node CC via node BA until it receives the token back, which it's going to do once node BA has sent that cell on its next hop. And then this is going to continue throughout the rest of this path. This prevents cells from kind of piling up in the final queues right before the destination, and that lowers our buffer pressure at each node. It also improves our performance. And we implement this in a very careful way that avoids deadlocking from happening. And in our implementation, we also use specialized queues, push and extract out queues, that enable us to avoid head-of-line blocking. Please see our paper for details. In order to evaluate this, we did packet-level simulations with 10,000 nodes, and we have several simulation parameters. I won't read them. We also compared to a number of baselines. We compared to several baselines as well as our own congestion control mechanisms. I won't talk too much about what these baselines are. Please see our paper for details. But let's actually look at some of the results. So this is for a short flow workload that primarily causes path collision congestion. And you can see that the blue line and the blue bar on the graph are doing really well. That is representing spray short. We're dramatically reducing our queue lengths, as you can see on the top graph, and we're reducing the flow completion times. However, if we combine hop by hop with spray short together, which is the green line and the green bar, that is doing the best. And in this workload, we actually outperformed all of our baselines. That's all I'm going to say about that. For the heavy-tailed workload, this one has a lot of longer flows, and it happens to create a lot of egress congestion. And here, hop by hop is doing really well. Again, if you combine hop by hop and spray short, that is when you get the best results. Here, for h equals 4, we did outperform all of our baselines. For h equals 2, one of them did somewhat better than us, but please see the paper for our discussion about that. Now I'll talk a little bit about our implementation. We implemented everything in an FPGA-based NIC prototype. We added several optimizations to reduce our memory requirements. And as a result, we achieve orders of magnitude less memory requirements than the existing systems. Unfortunately, I don't have too much time to talk about this, but please see our paper. And finally, I want to talk about something really cool that Shale lets you do, which is, for the first time, we have multiple schedules available for ORNs. And you can actually imagine kind of combining multiple schedules into a single overall schedule by literally interleaving the time slots. In this case, we've given half of the time slots to each subschedule, but you don't have to do exactly that. And when you do this, the overall throughput is going to be a weighted average of the throughput that each of these subschedules can support. And you are going to make the latency a little bit longer, but this is only for the intrinsic latency. The propagation delay is not going to be affected by this, and your queuing delay might be affected in actually really interesting ways because you're routing some of the traffic on some subschedules and other traffic on other subschedules. So this is something that you kind of have to tune manually. But we think this is a really exciting direction enabled by Shale, and we think it has a lot of promise. Finally, to summarize what we've talked about today, Shale is a new ORN design that supports tens of thousands of nodes. It has orders of magnitude better latency and memory requirements than existing designs at these scales. And we do this by using new schedules. They bring a tunable trade-off between throughput and latency. Each trade-off is Pareto optimal for ORNs, as we've shown in a previous theoretical work. We enable this using a new congestion control design that is specially designed for Shale's case. And we have an optimized FPGA-based hardware implementation. And I talked about interleaving, which is really cool. I'd like to thank my co-authors. Here are my co-authors. And I think all but one of us is here at SIGCOMM, so feel free to talk with us. Thank you so much. Happy to take questions.
Thank you, Daniel. Sir?
Hi, Matthew Grosvenor from Jump Trading. Once again, I'm always impressed by the heroic engineering that goes into these SIGCOMM papers, so well done for making this work at all.
Thank you so much.
One of the questions that I may have just missed as you were talking about it, but it wasn't clear to me, are all hops equal length? And if not, how do you deal with reordering in the network?
So all the hops, we model it as having the same propagation delay. We have thought a little bit about how you could deal with differing propagation delays, but we don't talk about it in this work.
Sorry, when I meant hop count.
Oh, hop count. Yeah, we do target the same hop count for all of our paths. In some cases, you may spray to a node that is matching the destination in one of the coordinates, and in that case, it would have one fewer hops. Reordering is a concern, and we just use a reorder buffer at the destination.
Hi, thank you for a great talk. So I'm Junyi from Huawei. So I have two questions. So first of all, in your presentation, you only seems that you only show the case for a single flow from one source to destination. So my first question is, if you have multiple destinations, for example, the node A needs to send multiple flows to B, C, D, and in this case, how do you choose between these flows? And yeah.
Yeah, no, that's a good question. In our simulations, the way we did it is you kind of just do a round robin between the outgoing flows that you have. We didn't get more complicated than that.
Okay, so you don't consider the position of the destination nodes, because I suppose in some rounds you may have some better choices.
Oh, I see what you're saying. Maybe if you're sending to a certain node, you might want to send some of your traffic because it'll have a shorter path at the specific point in time.
Yes.
It's a good question, but you'll notice we're routing we're doing valiant load balancing, and we're routing via an intermediate node that could be an arbitrary node in the system. So that ends up not quite being a concern in this case. It's definitely something we're considering for some of our future designs maybe, but in this case it doesn't end up mattering so much because the first spraying hops are the same regardless of your destination.
Okay, I see. And second quick question. So it seems that this scheme will cause a lot of out-of-order packets at the receiver side. So do you consider the reorder buffer as memory consumption in your evaluation?
Yeah, we don't consider it in this evaluation. It's something that we're thinking about for the future a bit more.
Okay, I see. Thank you.
Okay, great. Let's thank Daniel.